स्वागत है सभी का YouTube चैनल में, जहाँ पे आज हम देखने वाले हैं कंट्रोल सिस्टम का प्रैक्टिकल, जहाँ पे हम सीखेंगे बॉडी प्लॉट कैसे ड्रॉ किया जाता है विद द हेल्प ऑफ scilab. The outline of the presentation is frequency response, then we discuss body plot, in that steps for solving body plot, then body plot summary, single pole and zero body plot, a summary of body magnitude and phase plot, and lastly we discuss example to be solved using scilab. The first, frequency response. The transfer function can be separated into magnitude and phase angle information like h of omega, that is equal to, this is a magnitude form, h of j omega, and this is the angle of omega, where h of j omega is nothing but indicate of z of j omega. This is first one is a magnitude plot and second one is a phase plot. This is the sample of the body plot that can be done with the help of semi-log axis body plot paper. Bode plot. Bode plot is a semi-log plot of the transfer function magnitude and phase angle as a frequency, as a function of frequency. The gain magnitude is many times expressed in terms of decibel. That is decibel that is equal to 20 log base of 10 into magnitude, where A is the amplitude or gain. A decade is defined as any 10 to 1 frequency range, and octave is any 2 to 1 frequency range. Like 20 dB per decade indicates 6 dB per octave. Straight line approximation of the body plot may be drawn quickly from knowing the poles and zeros. Response approach minimum near zero and response approach maximum near the poles. The overall effect of constant zero and pole in terms of table is given as sum magnitude break, asymptotic magnitude slope, asymptotic phase shift. If constant k, then magnitude break is not eligible, then asymptotic magnitude slope is 0 and phase shift is 0 degree. If it is 0, then upward direction is plus 20 dB per decade and asymptotic phase shift is plus 90 degree. If it is pole, then it is downward minus 20 dB per decade in magnitude slope and minus 90 degree in phase shift. Here is the transfer function standard form, where h of j omega is k, j omega term plus or minus n, 1 plus j omega tau, then in bracket of second order pole, similarly kind of in the denominator that 1 plus j omega tau and the second order pole. Then there are 4 different vectors: constant gain term k, then poles and 0 at origin j omega m plus 12, poles or 0 of the form 1 plus j omega tau, and quadratic poles or 0 on the form of 1 plus 2 zeta j omega t plus j omega t square. Bode plot. We can combine the constant gain term k and the n pole or 0 at the origin such that the magnitude cross 0 dB. Like poles k divided by j omega raised to n omega 0 dB, that is equal to k raised to 1 by n, and it is 0, then k j omega raised to n is equivalent to omega 0 dB, that is equal to 1 by k raised to 1 by n. Define the break frequency to be a omega is equal to 1 by tau with a magnitude at plus or minus 3 dB and phase at plus or minus 45 dB. Now this is the steps for solving body plot. First, bring the given g of s, h of s transfer function into standard time constant form. Replace all s by j omega to get frequency domain transfer function. Make a table of the standard factor present in the given transfer function. Now analyze the table of factors, then make the table for plot representing the magnitude variation. We can take help of this table to plot the magnitude curve. Then select proper x and y scale for the magnitude plot. Draw the lines of the corresponding factor from the starting point to the corner frequency like the end point. Then note down the phase angle table and obtain phase by actual calculation. Then step 8, prepare the table containing phase angle variation and then obtain resultant phase angle by actual calculation. Step 9 is, depending upon the highest frequency term present, choose the starting point in the log scale, plot the point as per the phase angle table, and then draw smooth curve for phase angle plot. Then one of the important calculations is gain margin calculation, step number 10, and phase margin calculation is step number 11. So in gain margin calculation, from phase resultant curve, find omega, where phase crossover frequency, phase cross minus 180 degree. This is called the phase crossover frequency omega suffix pc. Draw the straight line from omega pc towards the magnitude plot till it intersects magnitude curve, and this point is called g. The difference between 0 dB and magnitude corresponding to point g is gain margin. Then phase margin calculation. From magnitude resultant curve, find omega where resultant cross is 0 dB. This is called gain crossover frequency. Draw the straight line from omega gc toward downwards till it intersect the phase curve, and that calls the point as P. The distance between point P and minus 180 degree line is the phase margin. This is the Bode plot summary in terms of factor, constant, pole or zero at origin, first order pole and zero, and quadratic pole and zero with reference to magnitude behavior and phase behavior. Like constant, then 20 log 10k for all frequency, then phase behavior 0 degree for all frequency. Pole at origin, then plus 20 n dB per decade for all the frequency with a cross of frequency 0 dB at omega equal to 1. Phase plus or minus 90 degree for all frequency. First order poles are 0 dB. Then bracket plus or minus 3 n dB, asymptotic plus or 20 n per decade for low frequency 0 degree plus or minus 45 degree n with slope of 45 degree n per decade, and for asymptotic plus or minus 90 degree n. Similarly, for quadratic pole, that is seen at plus or minus 40 n dB per decade asymptotic, and for break plus or minus 90 degree n, and for asymptotic it is plus or minus 180 degree n, where n is the number of root of value of tau. This is the in terms of statement that term constant k, magnitude 20 log 10k, phase k 0 degree, k less than 0, then plus or minus 180 degree. Plot at origin 1 by s, that minus 20 dB per decade passes to 0 dB at omega, minus phase is 90, 0 at origin s, that plus 20 dB per decade plus 90 degree, then real pole 1 by s divided by omega plus 1, then do the asymptotic at 0 dB, then do the high frequency asymptotic minus 20 dB per decade and connect line at omega 0. Then similarly you can proceed for phase like for asymptotic 0 degree, high frequency asymptotic minus 90 degree, and connect with a straight line from 0.1 omega naught to 10 omega naught. And this is the real 0. So in real 0 it is a plus 20 dB per decade and angle is plus 90 degree. Similarly you have to find the underdamped poles for quadratic poles and quadratic 0. Like underdamped poles calculation with minus 40 dB. If it is underdamped 0, then that is asymptotic plus 40 degree. In phase it is minus 180 degree, and in the 0 it is a plus 180 degree. This is the simple single pole and zero Bode plot, like gain 0 dB, then it is the pole, so it is minus 20 dB per decade. This is a phase plot. Start from 0, then minus 45 degree, this is a break, then minus 90 degree. This is the zeros at omega z 1 by tau, in this case plus 20 dB per decade, and from 0 to plus 90 degree. So now we have to solve example with the help of scilab. So first is g of s h of s given as like 10 divided by s into s plus 1 s plus 2. Then second is g of s h of s 100 into 1 plus s divided by 10 into 1 plus s divided by 100 divided by s square plus s plus 4. And third one is the g of s h of s equal to k divided by s into 1 plus s by 4 into 1 plus s by 40 for k equal to 4. Okay, so we have to solve one by one with the help of scilab. So this is the first example. Find the Bode plot of this for the system one, that is g of s h of s equal to 10 divided by s plus 1 and that s plus 2. Okay, so write the code for the same. CLC clear, then numerator that is equal to poly, and constant is 10 s, so s, and here we have used coefficient, so coefficient. So this is matrix 10 matrix generates as numerator 10, then s represent polynomial in S, then coefficient represent coefficient in polynomial S. Okay, then denominator answer, that is equal to polynomial of, here we have used roots, so it says 0, -1, -2. Then for the s plane, so s, here we have used the roots, so matrix 0, -1, -2, generate poles of the system. Then s represent the polynomial s, and roots represent roots of polynomial in S. Okay, then define system with the help of SY system linear function. Just change the first one, system SY1 here, first for continuous, then numerator, and second is denominator. So this is C for continuous, and generate transfer function. And then here we have used scilab, that is for clear and reset a figure or a frame with UI control. Then finally we have used Bode inbuilt command that generate Bode plot of this particular system. So Bode of the system with the frequencies like 0.01 to 100. You can select any values. This is the Bode plot of the system. Okay, then yes, then save this program, then run this program, and there is the first figure in front of you. That is a Bode plot of the system. This is the magnitude plot, and here you can select with the like data toggle data key point is there. So when you select this, then you can select or see any value in the magnitude plot. Similarly, you can see here also in the phase plot, and you can see the different value in the phase plot. Okay, so this is the first Bode plot of the given system. Okay, now this is the graphic window. Now we have to solve second example. So second example is that the second is g of s h of s equal to 100 into 1 plus s divided by 10 close, then another bracket 1 plus s divided by 100 close, divide by s square plus s plus 4 bracket s square plus 4. Okay, so now this example to be solved with the help of direct rational matrix. How? Let's see. So first LCM clear, then s equal to percentage of s, that indicate polynomial in s. Then direct we have used g, that g equal to in bracket 100 multiplication of 1 plus s divided by 10, then in other bracket, so multiplication of 1 plus s divided by 100. Okay, so that is the first one, and divide by s square plus s plus 4 square plus s plus 4. Okay, so that is the bracket. All bracket is closed. Once again, 100 multiplied by 1, you have to just check the bracket. So 100, then 1 plus s by 10. Okay, you can select here also. Then 1 plus s by 100. Okay, that is complete. Then s. Okay, that's why I have to remove this bracket from here. So this is rational matrix form. Rational matrix form. Then directly have to do the system, and here C comma G. Okay, so scilab system, and we can check the result for the second. You can see the Bode plot of the second figure. So this is the figure Bode plot. First indicate the magnitude plot versus frequency, that dB versus frequency, and second is the phase versus frequency. So when I click on the toggle data keep mode, then you can check the different value at the different location in the frequency. So this is the way you can also check in the frequency plot. Okay, so this is the way you can check the different value of the phase versus frequency in the frequency plot. So this is the second example. Now look at the third example. So that can be also solved with the help of this rational matrix. So in the third case, g of s h of s equal to k divided by s into s plus s into 1 plus s divided by 4, and other bracket 1 plus s divided by 40. So this is the way we have to complete this example. In this case, k value is for k equal to 4. So CLC clear, C s equal to percentage s and polynomial s. You define k equal to 4, or you can directly multiply it. So okay, this is given. So g of s h of s equal to k into, so just erase this, k into this k, okay, divide by bracket s into 1 plus s divided by 4, in another bracket with multiplication of 1 plus s divided by 40. So this is the okay, this is okay, so the bracket is closed. Okay, so now then system line generate the system linear function, then close or clear all the figure, then use the Bode plot. So let's run this command and see the Bode plot of this particular function. This is the third example. So let's see the result. As evaluate section. So okay, some error is there. You have to once again check the brackets. So here k divided by s, then s into 1 plus s. Okay, here a is 1 plus s divided by 4, then in the multiplication okay, So you have to 2 from the 1 plus s to the 40. Okay, so bracket is closed. Okay, I think now it's clear. So first save these and run this. See the result. So this is the Bode plot of the third system that represents magnitude versus frequency and phase versus frequency in the semi-log axis. You can check the different value with the help of data point and on the magnitude as well as in the phase plot. Hope you like this video. Thank you.